Hello once again. Welcome to another exciting episode of Dave Does Math from Home. Today we are talking about section 4.4, which is exponential and logarithmic equations. So we've already done exponential and logarithmic functions. We graphed those, we looked at the transformations, shifts, stretches, flips, all that stuff. In section 4.3 we dealt with properties of logs, and in doing so we reviewed the properties of exponents. So now it's time to look at what happens when we put these things in equations with variables in awkward places, and we try to solve for those variables. We're going to start with the super basic ones, things that we've already talked about in spirit, and those are things like 3 to the x equals 27. You can kind of just look at this and know that the answer should be 3. 3 cubed is what gets you 27. And you can kind of know that because of things like this idea, this format, is what we were thinking about when we saw things like log base 3 of 27 equals what? When we first introduced logs and we were looking at problems like this, I was encouraging us to think about this in terms of what exponent can I put on top of 3 to get 27, which is exactly what this thing is asking. What exponent goes on top of 3 to get 27? And the answer is pretty clearly x should be 3. So, I'm going to, even though this is clear, I'm going to add a step so that we can generalize from that extra step what to do in more weird situations. One way to think about this is to write both of these things as powers of the same base. So here we have a 3 to the x is 27. I can write as 3 cubed. This marker's not really doing it for me. 27 is 3 cubed. So, by expressing both of these terms as powers of the same base 3, that makes it extra super clear that x should be 3. And this express both sides as powers of the same base idea is what we're going to use to solve the first major sort of category of exponential and logarithmic equations that we're going to deal with. So let me erase the board a little bit and we can start talking about an example of that. Let's look at something like 36 to the x equals 216. This, as written, is not extremely clear. It's not immediately obvious that you could raise 36 to a power and get 216. But if we're being very astute, we might notice that 36 is a power of 6. And some quick math on a calculator should probably convince you that 216 is also a power of 6. So we can express both of these terms as powers of the same base, and then from there we can just do some properties of exponents mathematics, and then the answer should be pretty forthcoming. Here we have an exponent raised to another exponent. I know that in this situation you multiply them. And if I have 6 to the 2x is the same thing as 6 cubed, if the bases are the same and the result is the same, it must be true that the exponents are the same. This is sort of the big step we have here. And this is saying that the exponents must be the same because they have the same base and they're equal. That's sort of like the logical, intuitive explanation for why we can do this. If you're not satisfied with the logical, intuitive explanation and you want a more algebraic explanation, the algebraic explanation is you take the log base 6 of both sides. The log base 6 of 6 to the 2x is 2x, and the log base 6 of 6 cubed is just 3. So taking the log base b of both sides of the equation will sort of delete the exponential pieces from it and just leave you with the exponents. Or you can just reason intuitively that if they have the same base and they're equal to each other, their exponents must also be equal. Either way is fine. And from here, the problem is very simple. Just divide both sides by 2. Because at this point, what you have is a linear equation. And we all know how to solve linear equations. They are extremely straightforward. Ultimately, this is pretty much the goal. We're going to try really hard to transform these exponential and logarithmic equations into linear equations. If we can get them into linear equations, then we're all set. We can just solve the linear equation. Super easy. Not much more work than that. So let me erase all of this and we can do another couple examples. Start with one more pretty basic example. We'll use 8 to the x equals, let's go with 8 to the x equals 4. This is a little different than the other examples because this is less than 8. So, if we're going to start this, first thing we should do is express both of these as powers of the same base. The base that connects 8 and 4 is 2. So I'm going to turn the 8 into 2 cubed and the 4 into 2 squared. I'll leave the x on top of this. So here we have 2 to the 3x equals 2 squared. And again, you can either take the log base 2 of both sides, or you can just reason that if these are the same, then the exponents must be the same, and you get 3x equals 2, and x should be 2/3 from this linear equation. A more exciting example might look something like this. Five to the 2x plus 4 equals 125. Actually, let's make this even more interesting. No, this is fine. 5 to the 2x plus 4 equals 125. This seems like a good one. If we're going to solve this, we should first express both sides as powers of the same base. 5 is fine by itself. I'm just going to leave that alone. 2x plus 4. 125, I can call that 5 cubed. This means that 2x plus 4 equals 5 cubed, and I should get something like, no, I'm sorry, 2x plus 5 is just 3. The 5 goes away. So I need to subtract 4 from both sides. 2x equals -1. X equals -1/2. Because from here, you have a linear equation. I'm going to repeat that every time we hit that linear equation because that is really the goal of all of this. Exponential and logarithmic equations are hard, they're messy, they're weird. If we can transform them into linear equations, those are easy, straightforward, and nice. So that's what we're going to try to do every time. Do one more example of this. we'll migrate to some weirder stuff. I've used 5, 6, 2, 3. I guess I could do a 4. Let's think of an example with 4s. Let's do 64 to the 7x minus 1 equals 16. Seems like a good one. Both of these things are powers of 4, so we'll call this 4 cubed to the 7x minus 1 equals 4 squared. So properties of exponents, I can simplify this. This will be 4 to the, I have to multiply these. So we'll get 21x minus 3. You have to distribute this 3 to this entire exponent. Equals 4 squared. So 21x minus 3 equals 2. This is my linear equation. 21x equals 5, and x equals 5 over 21. Not a very pretty number, but it's not bad. It's a fraction. Don't have to get into weird decimals to do it, at least, and that's a plus. Speaking of getting into weird decimals to do these, stay tuned. It's going to get a lot weirder in part 2.